Hi friends, in the previous session we discussed about how to design some simple deterministic finite state machines. In this session we'll discuss some more languages for which we will be designing the DFSM. Let summation be A and the language contains all possible strings whose length mod 3 is equals to 0. Then the possible strings in this language are a raised to 0, a raised to 3, a raised to 3 means 3 a's mod 3 remainder is 0, a raised to 6, a raised to 9, a raised to 12 and so on. A raised to 0 means epsilon is accepted, then 1a is rejected, 2a is rejected, 3a is accepted. Again 4 number of a's, 5 number of a's are rejected, 6 number of a's are accepted. So how to design a DFSM for this particular language? Initially, as you know, initial state will be the final state because first string to be accepted is 0 number of a's. Assume this as state 1. Next it will go to, for 1a it will go to state 2. Now tell me, is this a accepted? Yes or no? Single a according to this language must not be accepted, so it is not in the final state. Then what about the second a? If 2 a's, then also it must not be accepted. So again a transition from state 2 to state 3 for a, which is a second a, and you can see here it is still in the intermediate state. Then coming to the third a, the third a must be accepted. So what we'll do? We'll take a transition from state 3 back to 1 with input a. So now you can see here, initially a raised to 0 means 0 occurrence of a's. So initial state is the final state, string is accepted. Next, a single a, 1a is rejected, 2 a's rejected, 3 a's reaches the final state, the string is accepted. Similarly, fourth a not accepted, fifth a not accepted, sixth a is accepted. So in this way, this DFSM will be accepting 0 number of a's, 3 number of a's, 6 number of a's, that is all the strings of a's whose mod 3 is equals to 0. So this is how to design a DFSM if such kind of languages are asked. If the same language is asked for two symbols, in the previous example we have seen for A. Now if it is for A and B, so whatever may be the string of A, a combination of A's and B's, its mod 3 must be equal to 0. So the possible strings in this language are w raised to 0, that is epsilon, string of a's and b's whose length is 3, AAA, AAB, ABB, BAA, any of these will be accepted. Then string of length 6, string of length 9, string of length 12. So the same logic will be applied. So let us see how to design it. Initial state will be the final state. Then previously had written A. Now here we'll write A or B to state 2. So first symbol is rejected. Second A or B is also rejected. Third A or B is accepted. I hope it's clear to you. Previous one we had one single A. Here we have A or B, one A rejected, A or B, second A rejected, A or B, third reaches the final state. Fourth symbol not accepted, fifth symbol not accepted. Coming to sixth one, it reaches the final state. And this is the DFSM designed for the language containing all possible strings of A's and B's whose length mod 3 is equals to 0. We'll take up one more example which is slightly a bit different from the previous example. In the previous example, we had the language of strings containing A's and B's whose length mod 3 is equals to 0. Now we'll go for designing a DFSM for the language containing all strings of A's and B's whose length mod 5 is not equal to 0. It means, what are the possible strings in this language? Will it accept the string with length 0? 0 mod 5 is equals to 0, whereas this string does not belong to this particular language. So it means W raised to 0 is not accepted. W raised to 1, string length 1, 1 mod 5 is 1, which is not equal to 0. This is accepted. Next, W raised to 2, accepted. W raised to 3, accepted. W raised to 4, accepted. Coming to W raised to 5, 5 mod 5 is equals to 0, whereas in this language it is not equal to 0. So W raised to 5 is not accepted. Similarly, 6, 7, length 6, 7, 8, 9 strings are accepted, whereas length 10 is not accepted. So in this way it will continue. String length 0 is rejected, length 1, strings of length 1, 2, 3, 4 are accepted, string with length 5 is rejected, then string of length 6, 7, 8, 9 accepted, 10 is rejected. So this is very simple now to design. So let us design it. This is your initial state. Will it state 1? Will it be the final state as before? No, because string length 0 is not accepted. So this will be an intermediate state, not a final state. Then from this state we'll have a transition for A or B going to state 2. String length 1, will it be accepted? Yes. So state 2 will be the final state. String length 1 is accepted now. Then what about string length 2? A or B going to state 3. So string length 2 is also accepted. Next, string length 3, A or B reaching to state 4. So 4 is also final state, because as you know, string length W raised to 1 is accepted, 2 is accepted, 3 is accepted. Okay. Similarly, if I go for 4, what about string length 4? String length 4 also must be accepted. So from 4 state Let us design one more transition. Take A or B going to state 5 with this state as final state. I hope till it's clear till here. String length 1 accepted, 2 accepted, 3 accepted, 4 accepted. Now what about 5? Is 5 accepted? No. So what to do? As before, take a transition of A or B going to state 1 back to the initial state, which is an intermediate state, and string of length 5 is not accepted. Coming to string length 6 accepted, 7 accepted, 8 accepted, 9 accepted. Again string length 10 is not accepted. So this is the DFSM design for the language containing all the strings of A's and B's whose length mod 5 is not equal to 0. Let us see the next language, a language containing all possible strings of A's and B's with a condition that the string contains an even number of A's and even number of B's. Then, what are the possible strings in this language? First string will be epsilon. If I take 0 number of A's and 0 number of B's. Next, 2 A's and 0 B's. 0 A's and 2 B's. 2 A's and 2 B's at different positions. 2 A's, 4 B's, and so on. In the previous lecture, we have discussed how to design a DFSM for even number of A's or for odd number of A's and so on. So using those, we will go for designing the DFSM for this particular language. So let us start with the first string. What is the first string? Epsilon. That is, initial state is the final state. Initial state is the final state which has even number of A's and even number of B's. So epsilon is accepted. Next, coming to 2 A's. How to design for 2 A's? First A, if 1 A, then is the number of A's even? No. So I have odd number of A's. And what about B's? Even number of B's. That is 0 B's and 1 A. This is for first A. What about second A? Second A must reach the final state. So I'll take this back for A. So you can see here for string AA, first A, it is in the intermediate state as it is odd number of A's and even number of B's. For the second A, it is going back to the final state having even number of A's and even number of B's. So here number of A's are 2, number of B's are 0. So next, coming to number of B's. So A's are 0 and we have 2 B's. So how to design this? Let us see. Take a state, okay, wherein you have a B, one compulsory B. Means you have odd number of B's and even number of A's. For 1B, it is in the intermediate state. For the next B, it must go back to the final state. For the next B, it went back to the final state. So this string is also accepted. Then go for 2 A's and 2 B's. 1A, 2A, 3A, third B, fourth B, reaching the final state. Now this was in sequence. If they are at different positions, then AB, AB. So how will design for this? So in this state we have even number of A's, even number of B's, odd number of A's, even number of B's, even number of A's, odd number of B's. We'll take one more state wherein we'll have for this string AB, AB, A. Now I'll be having a transition B. It means odd A's, that is only one A, and odd B's. So as you see here, 1A, 1B. So while reaching here, you have 1A and 1B. So A, B. Next, I want to have A, B. So if I have A, it means I'll be having 2 A's, that is even number of A's and odd number of B's. Then can I come to this particular state? Yes. So I'll have a transition from here A. Now you can see A, B, reaches the final state, hence the string is accepted. Coming to B, A, B, A, B. So again, if I take a A here, B, A, and again a B, and a A reaches the final state. B, B, A, A, B, B, A, A. We will take one more string, 2 A's and 4 B's. 1A, 2A is in this state. 4 B's, 1, 2, 3, 4 reaches the final state, and hence the string is accepted. So this is the complete DFSM for the strings containing even number of A's and even number of B's. If you see in the previous DFSMs, whichever we designed, I just labeled the states as 0, 1, 2, 3, 4 and so on. In this example, I labeled the state with having even or odd number of A's and B's. So that when you reach the current state, the state says the A's and B's you have come across in the string. In this state, you have odd number of A's, even number of B's. In this, odd number of A's, odd number of B's. In this, even number of A's, odd number of B's. And in this state, we have even number of A's and even number of B's. So hence, this state will be the final state for the strings having even number of A's and even number of B's. If this language is changed to containing the strings with even number of A's and odd number of B's, then we go for designing the same DFSM, but the final state will be changed to this state. So previously we had even number of A's and B's as the final state, whereas in this DFSM, even number of A's and odd number of B's state, that is even number of A's and odd number of B's, this state will be the final state and rest all will be the intermediate states. Similarly, for odd number of A's and even number of B's, this state will not be the final state. Odd number of A's and even number of B's. So here this state will be the final state and rest all will be the intermediate states. And last, the same way, for odd number of A's and odd number of B's, so same DFSM, but here this will not be the final state. All these three will be the intermediate states, and odd number of A's and odd number of B's, that is this state will be the final state and rest all will be the intermediate states. Next language to design is having all possible strings of A's and B's with the condition that every A is immediately followed by a B. It means I may have any number of B's. I may have an A, I may not have. But if I have a A, it must be immediately followed by a B. So the possible strings in this language are epsilon. I don't have any A's, a single B or any number of B's. If I have a A, then it must be immediately followed by a B. B, A followed by a B. A followed by a B, and so on. So how to design a DFSM for this particular language? As you all know, first string is epsilon. So initial state is the final state. Take the case state 1. Then if I have a A, so I must have one compulsory transition from state 1 to state 2 having A. If I have a A, then state 2 is intermediate because the condition is not yet complete. If I have a A, then it is immediately followed by a B. It means if I have a A, then it must be immediately followed by a B, reaching the final state. So this is the language. What it states? If I have a A, then it must be immediately followed by a B, reaching the final state, and hence the string accepted. Is this DFSM complete? No, not yet, because from both the states we must have one compulsory transition for A and B without violating the language. So let us do that, starting with state 1. From state 1 we have a transition for A going to state 2. What about for B? Can I take a self loop? Yes, I can, because there is no condition on B's. So I can have any number of B's reaching the final state and that string will be accepted. So from state 1, one transition for input A going to state 2, one transition for input B going to state 1 is complete. Coming to state 2. From state 2, I have a transition for input symbol B going to state 1. What about A? So for A, what to do? Can I have a A as a self loop here? No. We have to trap this A. Take a transition for A to the trap state or the dead state, and again from dead state A comma B. So this is the complete DFSM. A, B from state 1, A, B from state 2. Since I can't take this A transition into the DFSM, this is given to the dead state. Then from the dead state, self loop for A and B. What is dead state? Why we put the transitions to these dead states? I have explained in the previous session. So this is the complete DFSM for every A if exists is followed by a B. Let us design few more DFSMs with dead state or trap states. Here is a language containing strings of A's and B's with the condition that no two consecutive characters are the same. So the possible strings in this language are epsilon, a single A, a B, AB, BA, and so on. Condition is in these strings no two consecutive A's or no two consecutive B's can occur. So let's start designing the DFSM for this particular language. So first string in this language is epsilon. So initial state 1 itself is the final state. The next string in this language is A or a B reaching the final state. So A going to state 2 reaching to final state, a B going to state 3 reaches the final state. So A is accepted, B is accepted. Coming to AB. AB or BA must also be accepted. So A you have a transition from 2 to 3 with B reaches the final state, hence the string AB is accepted. Similarly BA reaches the final state. Next, let us balance the DFSM, complete the DFSM. If you see here, state 1 we have a transition A and a transition B. Coming to state 2, we have a compulsory transition for B. What about A? 1A already is there. One more A will not agree with this language. One more A will have two consecutive A's. Similarly, B from state 3, you have a transition A to state 2. If I take one more B, then there will be two consecutive B's. So we need a dead state or a trap state here. State 4, which is a dead state. From state A, transition A. State 3, transition B, going to dead state, again a self loop for dead state with transitions A and B. Now you can see A, B, B, A. Any combinations of A's and B's will reach the accepting states, whereas two consecutive A's or two consecutive B's go to the dead state, also called as trap state or dead state. So this is the DFSM design for the language containing strings of A's and B's with no two consecutive characters same. In this language, we are supposed to design the DFSM for all the strings of A's and B's which contains no more than one B. That is, it may have any number of A's but not more than one B, including epsilon. So the possible strings in this language are epsilon, a single B, 1A and 1B at any position, 2 A's, 1 B's, 3 A's, 1 B's, any number of A's, etc. So let us see how to design the DFSM for this particular language. Initial state being the final state, state 1 for string epsilon. Then if at all B exists, there must be only one B. So let us take a compulsory transition B to a next state, state 2, which reaches the final state. So the language is satisfied that if string does not occur, then initial state is a final state. If the string occurs, then at a max it can have only one B. But you can see here there is no restriction on number of A's. So I can take a self loop at both the states for input symbol A, as there is no restriction on number of A's. Now let us check whether the DFSM is complete, starting with state 1, one transition for A and one transition for B. So state 1 has both the transitions. Coming to state 2, one transition for A is there. What about B? Can I take a self loop here? If I take a self loop, it will be more than one B's. If I return it back to 1, again there also I will be having more than one B's. So what to do? Only solution is take a dead state, move the transition from state 2 for input symbol B to the dead state, and again from the dead state compulsory transition for A and B. So this is the complete definition for design for the deterministic finite state machine. Let us design one more DFSM for the language containing the strings that does not contain substring AAB. If you recollect, in the previous session of DFSM, we have designed the DFSM for this language having substring AAB, a DFSM which accepts all these languages, and the DFSM we designed was this. But now we have to design the reverse of it, that is strings that does not contain substring AAB. So if question asked, then how to design such type of DFSM? It's very simple. Let's start designing. So first step is to design the DFSM for containing substring AAB, that is the same DFSM. So let me design once again. 0, 1, 2, 3. 0 initial state, B, A, B, A, A, B, A, B. So once we are done with this, second step is interchange the intermediate states to final states and final states to intermediate states. That is, in the previous DFSM containing the substring AAB, final state was 3, intermediate were 0, 1, 2. Now, in this DFSM which does not contain substring AAB, what we have to do is we have to make 0, 1 and 2 as final states and 3 as state 3 as intermediate state. So this is a DFSM for the language which does not contain substring AAB. I hope you understood how to design the DFSMs. Thank you.